Alright, welcome back to making a synthesizer in C. Oh, this is episode 3. Right, so when I was reviewing the last episode, I actually noticed that our update oscillator array doesn't actually handle the different shapes we've been making. So you remember we made a sine wave, a sawtooth wave, and a triangle wave. And then in our handle audio stream, whenever the audio stream needs to process a new block of samples, we're updating it 3 times, once for the sine waves, the sawtooth waves, and the triangle. But we then actually need to handle that, because it's still, if we look to accumulate signal, it's just doing triangle waves at the moment. So let's go ahead and handle that. Oh, okay. So what we need to do is, you know what, I'm going to get rid of this accumulate signal function and pull it into the oscillator array, because that's the only place it gets called. So there's no point having it as 2 separate functions. So what do we need? We're looping over the oscillator. So already you can see a bug here where we're setting the frequency on oscillator, but this is actually an array of oscillators. So I'm going to call that oscillator array, just to be clear that we then need to do oscillator array I and then set the frequency. And then for the sample, we need to update the LFO. Each oscillator has its own LFO. And then oscArray I, that needs to be a pointer. And oscArray I, LFO. So this is for the sine wave case. So now we need to do one for the triangle wave case. So this will be update oscArray sine, and this one will be, actually we'll do the sawtooth first. So this just becomes sawtooth wave. Now we're already seeing duplication. Like all this logic, if we ever want to change something here, we're going to have to remember to change it here. So shall we deduplicate this? The only thing different between these two functions is this. So this lets me introduce function pointers. What I can do is instead of telling it to call this specific named function, I instead pass in a pointer to a function. So this can change to whatever we pass inside our list here. So this, get rid of that because now it just becomes just a generic updateOscArray. Synth oscillator. I'm going to make it the first. So we want something like wave shape fn function. Fn short for function. Just call this wave shape. Is this the wave shape f function? So we need to define what that looks like. So we do that with, yeah, function pointers in C. They always look rather peculiar. You start off, it looks like a function which takes in an oscillator. So this is called a function signature. And you notice if I get rid of the name, because the name is just there for us to be able to refer to it, they all have the same signature. So what I'm doing here is creating a type that refers to that specific signature. To do that, we have to wrap the name and then put a star behind it. That's just the convention in C. That's how a function pointer is defined. So that takes in a wave shape function, and then this just becomes wave shape fn. So that's updating. So an oscillator has a sine wave is a bunch of oscillators. Oh, it's not that, it's this. It's synth. Wait, yeah. Yeah, it's the oscillator frequency, but then it's the synth LFO. There's one low frequency oscillator that drives the numerous bass oscillators. And then updateOsc does that. Is that correct? I don't think it is. Because don't we want to... So where do we actually apply that to the signal? We need to accumulate. So yeah, we're just missing the accumulation step. So that's synth signal t equals, oh, I'm doing this in the wrong function. Let me get rid of this one. Synth signal t, and then it's the wave shape function, and then we pass in OscArray I, and it's plus equals because we're accumulating. Now we're using the same, we might want a different shape for the LFO. So this would then just be the base oscillator shape, and then the LFO shape. And now this becomes the base oscillator shape for the sine is sine wave os. And I'm going to do sine wave for the LFO as well. So we have sawtooth, and we'll do sine wave for all the LFOs just for now. Then we got the triangle. Sine wave. So that all looks good. For oscillators, yep, fine. Let's give this a run, see how it feels. Make sure audio isn't too high again. Yeah, we set that really low, didn't we? Make it a little bit higher. Build, then run. Here we go. Uh-oh, error 67. Let's go to line 67. Expected, comma, got base osc shape function. Does this need to be a pointer? Is that what's going on there? Well, I never. Why? Do we need to... Another way we can do this is pull that out and do a type def. So this is a pointer, function pointer, pointer expected, 75. And then the OscArray, I, frequency. We move this all the way up to there, just clear. What is going on here? Alright, in a situation like this, can't remember everything about a language, so trusty Google. I'm just going to Google how to do function pointers in C. Function pointer, geeks for geeks. In C, like normal data pointers, int, char, etc., we can have pointers to functions. Following is a simple example that shows declaration and function call using function pointer. This is the normal function. Fun pointer is a pointer to function fun. So do we need to... Oh, of course, we forgot the ampersand. Although I assumed that it automatically infers that you're trying to do a function pointer, but that assumption was probably wrong. So basically you need to put an ampersand between each of these to say, hey, this is a pointer to that function. Probably not. Oh, we don't need the name of the argument, because again, the names are just there for us as labels. See if that works. Still no. Let's go back, read more. Let's do type def function pointers and see. Understanding type def. Okay, so we got the signature on, so this does go here.
I'm just reading this example code. See, they're not putting a star because it's already a pointer. The type is a pointer. Oh, it's referring to this line though. I see it. We don't want this arrow here. So, let me explain. If oscillator was a single object, this is a pointer to a single object. Well, to access, we can't do dot frequency because basically in memory, this oscillator is a number, some random number that points, this number is referring to an address in memory. If you imagine in memory, almost like a spreadsheet, it's referring to a row and a column to then look, and the value is in that. So that's why we do the arrow. To say, hey, we need to look at this address and then jump to that location to find the actual data, which is the frequency. But when oscillator is an array of values, this brackets and a number inside is doing that jump. This brackets is doing the logic of the arrow. So now that we've actually got to that specific place in memory, we can now use the dot notation, dot frequency. So that's the mistake I was making. So we need a dot there. Synth is a single object. We need an arrow. Oscillator, we're doing the jump to memory, so then we need to get that memory location because this expects a pointer. So this also needs it because this expects, the wave shape function expects a pointer to an oscillator. So that should now work. Fingers crossed. Cannot cast struct anonymous to struct anonymous 79. This needs a pointer. $100 sawtooth osc. Oh, the function is called sawtooth wave osc. 101. If you got a comma. Finally. Cool. All right, let's again, we'll simplify it down to 1. Cool. So another thing we can do now is say, so this was setting the amplitude to all of them. And if we remember the logic here, we're setting the first oscillator, num oscillators minus I, so the first oscillator would equal num oscillators. Let's go back to an example of 4. So this
whole expression, if this was the first oscillator, it would come to 4, and then it would be times 1 over 4. So we do that. Well, if we do 1 divided by 4, obviously we'll get 4 again if we times that by 4. So this all wraps to 1 times 0.2. If this was the second oscillator, we'd get 4 minus 1, because don't forget I starts at 0, so we get 3 times 1 over 4, so we get 0.75 times 0.2. So each one gets lower and lower. That makes sense. But then we could say, hey, let me get rid of this one. If you just wanted to make the sine wave louder, we could minimize the other two shapes. Maybe we need to really minimize them. I have a feeling amplitude isn't getting set correctly. So the amplitude lives on the oscillator. Let's have a look. Yeah, look, we're only doing amplitude on the sine wave, not the sawtooth and the triangle. So we'll do that. Or maybe we pull it out of the actual shape function and do it here. So then it becomes OscArray and amplitude. There we go. So we can come back to where we were setting the volumes, pump these up a little bit. Let's just play with some different numbers. I'm going to change the way this renders now because we're drawing pixel by pixel. I'm going to make it into a line. Let's see, let's get our Raylib cheat sheets. Let's have a look at this. Line, 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 line. We're looking for the shapes. So we can either draw single lines, there's a draw polyline. Oh, that's drawing a regular polygon. So just like a draw a list of lines. Draw line sequence, draw a line strip. Takes in an array, or a pointer to points, the number of points, and a colour. That is exactly what we want. Yoink. And then we come down to our drawing code where we do a draw pixel. Really what we want is a vector 2. Call this points or signal points. How many is going to be the same size, which is as our, is it buffer? Stream buffer. Stream buffer size. And then for each one, we're going to say signal points I.x equals I. Make that float. I.y equals this one here. And then I copied it and then I never draw a line strip. I'm going to pass in signal points and we're going to make it good old red. Right, so this is drawing the signal. Oh, that's nice looking, isn't it? So if we come back to our to-do list, that's done. Fix the way the signal is rendered. We've improved it. I think we can improve it more because it's stable in some places, but in other places it goes a bit wacky. I think what we can do is tell you what, I'm also going to draw a line as like the horizontal 0 point. So what's that going to be? It's going to start at x0. The y needs to be half, and then it's going to end at screen width, and then the y would be the same, and then I'm going to make that, I don't know, what colours? What are colours even? Something like, is it like a dark red? Or just dark grey? Should be fine. So this needs to be, tell you what, let's hoist this up. Screen height over 2, so I'm going to call this const float screen vertical mid point. And these just become both screen vertical midpoints. Right, so here's our waveform. What we can do is look for, let me try and find a stable. There we go. For when the signal drops from positive to negative, or vice versa, if it goes from negative to positive, we'll actually start rendering from the first time that happens. That's called a zero crossing, because the waveform crosses the 0 point. So we're going to pin basically to the left side of the screen at the first 0 crossing. Hopefully that should help. So how can we do that? Might need to change the way this is constructed. So I'm going to create a new block, and we're just going to create a size t I, and we're going to start at 1, not 0, because I need to compare this value from the last value. So we're going to use a new loop format called while. So how a while works is everything between these braces are going to loop over and over again while what's in here evaluates to true. So we're going to have a counter that does start at 0. So while the counter is less than the stream buffer size, I'm not going to do that for now. Just make it explicit. I'll say counter plus equals 1 in the loop. Let's see. Let's go back. So we need to check if signal I, what case? We're going to go when it goes from negative to positive, is greater than or equal to 0 and signal I minus 1 is less than 0, then we have a zero crossing. So if that's true, we can start adding points into the signal points vector to array. And at this point, we want to start incrementing our counter. We also need to say if I ever reaches stream buffer size, then I needs to go back to 0. Now there's a potential infinite loop that could happen if the signal never goes above 0, which shouldn't happen with a cyclical signal. Then this block will never enter, so the counter will never increase. So this will always evaluate to true. The counter will always be smaller than the stream buffer size. So we're going to need to keep another one, which is the call this the loop prevention counter. So this will get increased outside. And our loop prevention will just be like, as long as our loop prevention counter is less than stream buffer size times 2. And then we draw the line if and only if our counter is equal to stream buffer size. Actually no, because then this would become 0. So I wanna put this at the top. Let's see if that works. Obviously not. Let's have a look. So I is equal to 1. Oh, actually, if it's does mean we're never going to insert sample 0. The better way to do this is as soon as we find the 0 crossing, we stop the loop. So we just say, like, instead of doing all this, let's just say our 0 crossing index is equal to 0. And then as soon as we find the 0 crossing, we set the 0 crossing index to I. Get rid of this loop prevention thing. Get rid of this. And hoist this out. And then we want to say and then we will do a loop. So for we're going to use a bit of modulo mathematics. So our actual index, so our point index, idx short for index, is going to be I plus the zero crossing index modulo the stream buffer size. So it will wrap around like a clock. And then this becomes point index. And then yeah, we keep I. No. This becomes I. This becomes signal index. And just to make it a bit clearer, I'm gonna, instead of calling it I, call this the point index. And then the signal index is here. This can get, again, it's good to keep related data near to each other. We'll set counter to 1 as well, or counter to I. Oh, there we go. I think we got our first infinite loop. This needs to go outside the if. We don't need to do this if counter. Well, because if we can't find the zero crossing, then it's just going to start from 0. Still not working. Why? Why? Also bring this down. Greater than 0, less than 0. 0 crossing, and then we break. So we exit this loop. Point index 0, point index plus plus. Signal index equals point index. I'm using the high here. Okay. And then again, that needs to be point index. There we go. So, still not quite. So that shouldn't be scrolling like that, I don't think. Let's draw some more text at 10:30. 0 crossing index is equal to I oh, you know what? I don't need to do a while loop here. It's causing more issues than it's worth. I think this can be a for loop. We can do for size ti, start at 1, end at the end, which is stream buffer size, I++. Then we can get rid of that. That's a lot simpler. But yeah, we'll still print it just to see. Xerox. There you go. So it still can be weird at times, but it should be a little bit more stable. But you can sort of get that pinning effect by how it like it shrinks and stretches. But that should be really obvious if I just clear out and only have sign. Yeah, can you see how it's pinned to the left side of the screen? Not sure why it goes a bit weird on the right side though. I guess that's because that's the point when it starts to wrap around. So obviously it's not going to line up properly when it wraps around. So I can show that by saying when we're actually constructing the signal points, we actually we only go up to stream buffer size minus the 0 crossing index, but it means we won't draw the whole. Or instead of doing that here actually, we could just do it in our draw line strip. We only draw that many points. But it does mean we get this. Depending on how chaotic the signal is. And let's make you triangle. Right, I was trying to play Mary Had a Little Lamb, but that was terrible. Cool, I mean, we can come back to this. Any other way to improve signal rendering? Who knows? So our next one is to add a graphical user interface. Actually, you know what? We never did a square wave. Let's do a square wave. So float square wave takes in an oscillator pointer. Square wave should be pretty simple because it's just either high or it jumps down to low. I'm not going to break out Audacity for this one. So, I mean, we could do like if osc.phase is greater than or equal to 0.5, we just return 1. Otherwise, if it's less, we return -1. There's a slightly more succinct way to do this logic. I could just do return, and this is called the ternary operator. So we put that, and then we put a question mark after it, and then we say 1.f and negative. So that's exactly the same as this. You can see here, this is the if this expression is true. Then we have the question mark, this is the ternary operator, and then if it is true, we return this value. And then a colon to say else, this is just a short way of saying else, return this value. I only use the ternary operator if it's a really simple line like this and it can fit on the line. Otherwise, I'd rather just do it in this more expressive form. So we need to, how do we add this in? Pretty simple. We just create square osc. We add it to our synth. Square osc. Then we just need to add another update. So this becomes square wave, OSC. Keep a sine wave for the LFO. Square osc. And then we'll keep it as just the base frequency. Or maybe base frequency, like square waves make good bass noises, so we could halve the base frequency. And then we need to set its amplitude. So let's set the sawtooth and the triangle to 0.5 and maybe this one to 0.25. See if this works. It did not. Well, I need to actually pass in to the simp structure. I mean, let's just clear out all the other ones for now so we can see the square wave. Yeah, we're getting that funky shape because of our LFO. So I'm going to set the LFO amplitude to 0 as well. Are we not using the LFO amplitude? Oh yeah, because we took... We need to times it by the synth LFO, that amplitude here. There you go. Nice. So now if we come back to our LFO and bump this up to what it was 10. Whoa. Weren't we controlling the frequency as well? So what if we just make it quite subtle? I want the LFO to go even slower at times. I like it. Let's half U. We'll do 2.5, 7.5, 0.75, and then all of the sine. Get some funky sounds. Sounds like a old school racing noise. The gear shifting sound. So you can imagine like using this real-time synthesis if you're doing a racing game and you could actually drive, rather than having pre-made sound effects, you could actually drive the sounds procedurally. Okay, this is a short one today. This is all pretty good. I think tomorrow we'll look at this GUI, and also I might talk a little bit about audio aliasing with the non-sine shapes, like the saw, the triangle, and the square wave. There's actually a hidden issue with them that I'll explain next time. Cool. I will see you in episode 4. Yes, 4. Bye.